Okay, let's start our today's topic. We will focus on a new modeling approach, which is very commonly used in biomedical research. This is called logistic regression. So first, I would like to introduce some basics about logistic regression. We will start with why we want to use logistic regression and how we fit these logistic regression models. And then we will look at two examples using the Framingham dataset we have used in the previous days. So let's start with the logistic regression. So previous 2 days, on Monday or Tuesday, we talk a lot about linear regression. So we have seen a few examples. For example, we have studied the relationship between age and blood pressure. And we study the relationship, for example, between the age, the running time, the max heart rate with the VO2 max. And we also study the cholesterol levels between people who are smokers and who are non-smokers. If you think about the common thing among those models, the common thing is they share the same types of outcome. Think about what the type of this outcome is. So think about, is this numeric types of outcome or categorical types of outcome? So let me use this. So for all of those examples, the outcome, no matter is blood pressure, the VO2 max, or cholesterol, they are all what? Numeric, right? My pencil didn't work. So numeric, in other words, they are continuous variables. And we can fit the linear regression to study the average of the mean blood pressure, the average of VO2, the average of cholesterol levels. But we know we have other types of outcomes. For example, we might have a study, like we want to know, did the patient develop coronary heart disease within 10 years? So the outcome is yes or no, right? Another example, was the tumor issues malignant or benign? Here we also have a yes or no types of outcome where we have malignant or benign. So those types of outcome is what we call binary outcome. Binary meaning it only includes two possible values, yes or no, malignant or benign, or another example, did the patient survive the surgery? Yes, survived. No, didn't, right? Again, two possible values. Did the screening test classify the subject as positive or negative? Again, two possible values, positive or negative. So those examples, we can clearly see the outcome is not continuous as the blood pressure, as the BMI, as the cholesterol, right? So in practice, when we have a binary outcome, we denote one possible values as the event and the other possible values as the non-event. Or statistically speaking, we use the term called success and failure to denote those two possible values. Let's look at the coronary heart disease, this example. If we denote have the disease as a success, then we will code the outcome Y as 1. So people who don't develop coronary heart disease will be coded as 0. Okay. And you may ask, can we flip it? The answer is yes. So if you define people don't have the coronary heart disease as a success, then those people will be coded as a Y equals 1. And for those people with disease, Y will be coded as 0. So it really depends on what you want to study. If you define one as a success, basically you care more about the probability of success. For example, if you define have the coronary heart disease as success, basically you are caring more about the probability of developing heart disease. If you care about the tumor, a benign tumor as a success, right? So we are talking about the probability for this tumor to be benign. Okay. So again, which one to code as 1, which one to code as a value of 0, it really depends on what you want. Okay. And the next important question is, can we use the linear regression we have talked previously to model the probability of success? Okay. Let me repeat this question again. Since we have the outcome, which is yes or no, right? Y, which we denote as either 0, as a value of 0 or 1, and we have our predictors X, right? So can we model the outcome as using a linear regression? So the short answer is no. So let's talk in detail why we shouldn't do that. So suppose we fit the probability of some event happens as a linear regression. Okay. On the right side, you will see it's a linear combination, right? Bit 0 is intercept, bit 1 is the slope. Basically, this is a straight line. So one question appear immediately is, let's think about what's the possible values of the probability pi. We know the probability goes from 0 to 1. But what's the possible values of a straight line? A straight line can go from negative infinity to positive infinity, right? So the range of the left side of the equation and the right side of the equation does not match, right? This is the first main reason why we should not use a linear regression for a binary outcome. So let's look at this plot. Suppose here, our outcome is X, our vertical axis is the probability pi, right? So let me try to make it easier for, let's use a word. It's really hard to write something on the PDF word. So let me do this. Okay. So, all right. Suppose we fit a linear regression, right? Horizontal axis is our predictor X, and vertical axis is our probability of success pi. We know pi goes from 0 to 1, right? If we fit a positive line, so the line looks like this, right? So at a larger value of X, those linear part goes beyond value of 1, and on the very small value of X, the probability goes below 0. Similarly, if we fit a negative line, right, we got the same issues. Suppose the line we fit is this. Now, at a smaller value of X, right, this side, the values goes beyond 1, and at a larger value X, the value is below 0. So that's one reason, right? We don't want to fit a linear regression. Another 2 reasons actually related to the assumption that we talked for the linear regression. If you remember the assumption for linear regression, we use LINE. L is for linearity, I is independent, N is normality, and E is equivariance. So the 2 last assumption will be violated if we fit a linear regression. Because for a binary outcome, we know the variance of the binary outcome equals the probability times 1 minus the probability of failure. The probability of success times 1 minus times the probability of failure. So this variance is not a constant number, which it varies for different values of pi. Okay, for different values of probability, we have different variance for the outcome. But for linear regression, we assume what? We assume equal variance. at all the conditional all the values of x, the variance is always the same. But for the binary outcome, that's not the case. Another reason is about the normality assumption, where we assume the residuals to be normality. But here, if we have a binary outcome, we know the outcome only takes value of 0 and 1. So if we think about the residual could only take 2 values as well. So this is obviously not a normally distributed residuals, right? So those two and 3, these are the assumptions which is violated for the linear regression. So because of all these 3 reasons, we need to come up a new method can address these 3 things together. We want the predicted probability bounded between 0 and 1. And we also want this model can handle the non-constant variance. And ideally, we want the output from this model has interpretable results. Okay. So one solution to address all these 3 questions is logistic regression. What logistic regression did is it did not fit the probability directly on the left side, right? Think about the equation. On the left side of the equation, it's not about the probability itself. Instead, it modeled a transform probability. Okay. So this transformation is what we call logit transformation. People also call it log odds. So here is the function of probability, logit function, which we can write as log of pi over minus pi. So we will talk about this shortly. Okay, this actually is what we call odds. So logit equals the log odds. So logistic regression did not model the probability directly. It modeled the log odds. And then on the right side of the equation, it is the linear combination as we did before. Now, why this work? We can think about the possible values, right? The range for the left side of the equation. So we know pi is from 0 to 1. So pi over 1 minus pi, it is a positive value, right? The number greater than 0. And if we take a log of a positive value, so the range goes from negative infinity to positive infinity, which is the same as the range on the right side of the equation, also goes from negative infinity to positive infinity. Great. So by doing this, we can, the range of both sides of the equation matches, right? And also, this logistic regression assumes the outcome y follows a binomial distribution. Let me write it here, sorry. Okay. The outcome yi follows a binomial distribution n equals 1 and probability pi. Or we can use it pi I, use the same notation pi I. And then we model the logit of pi I as a linear combination of predictors. So this part assure that the outcome follows a binomial distribution. So it allows an equal variance. Okay. So all those 3 questions or problems are solved by fitting a logistic regression. So any question here? All right. So this is the model we have, right? We have log, odds on the left side, and on the right side, we have a linear combination. So we can transform back to get the probability of event. So which is this equation. So probability of event equals this thing. Okay. All right, so let's look at a few patterns which relate to the slope of the predictors and the probability of the events. So suppose we have a positive slope. Okay, let's think about the example of coronary heart disease. So the pi here is the probability of developing a coronary heart disease. And x, let's think about as air pollution. Okay, some value of air pollution. Now we know, first of all, we can see the range of the estimated probability is bounded between 0 and 1, and that's good. And another thing is, suppose if we increase the air pollution levels and the probability of coronary heart disease increased a little bit, but then it increased much faster, but at the larger values of air pollutions, it levels off. The probability of getting coronary heart disease leveled off. So here we have an S-shaped curve. Actually, if you think of it biologically, it makes sense, right? At a lower level of air pollutions, maybe the probability didn't change too much. And with the accumulation of coronary heart disease, with the air pollution level increasing, and the probability arise more greatly, and at some point it levels off because the even more severe air pollutions does not improve the probability as much as what happens in the middle. Right? This is a common S-shaped curve relationship. And similarly, if we have a negative slope here, and this is the plot we got. First of all, let's check the range of estimated probability. It goes from 0 to 1. That's good. And now with x increasing, the probability is decreasing, right? And it also shows a S-shaped curve. All right. So next thing since here we have introduced logistic regression, the next thing is how we estimate the beta 1 and beta zeros, like here. Here is our logistic regression model, right? How we know what's the value of beta 0? How we know the value is beta 1? For the linear regression, we can estimate those beta 0 hat and beta 1 hat using the ordinary least squares. But in logistic regression, we will use a different approach, which is called maximum likelihood approach. Basically, the idea is we want to get the beta hat, which is the estimated parameter, so that the likelihood of the likelihood of the data will be maximized. So the likelihood will be as high as possible under these models. So that beta hat is what we call maximum likelihood estimation. Okay. So it's different than the ordinary least square that we introduced in the linear regression. All right. Once we know how we got this hat, right? And the next question is how we interpret beta hat. What does the beta hat represent? Or what does the beta hat tell us? So let's again start from the linear regression. Think about linear regression, the beta 1, the slope of the predictor. That can be interpreted as if we increase the predictor by 1 unit, how much does the average of y increase, right? For example, if we increase age by 1 year, what's the BMI? What's the average BMI will change? That's the slope in linear regression. While in logistic regression, it's similar, but just a little different. The beta 1, meaning if we increase the predictor by 1 unit, what's the change for the log odds? Okay, think about that. Hold on. So let me see. Okay. So let's write these two equations. Maybe this will help us to understand it. For linear model, right? For linear regression, we model the outcome as a slope and intercept form plus some errors. While for the logistic regression, right? We model what? The log odds, right? Log odds as a function of beta 0 plus beta 1 x. So beta 1 actually is if we increase x by 1 unit, how much does the log odds increase? Right? It's just similar as linear regression, but on a different scale, on the log odds scale. Okay. You might say, oh, it's really hard to understand because it's less intuitive. What is log odds, right? People don't, I mean, if you read the paper, you see with age increasing, the BMI will, the log odds of, let's say, obesity will will change by how much? That's really not ideal. I don't think people will understand that. Instead, to make life easier, we can transform back into the quantities that people are familiar with. All right. So here I will talk about the three different scales. The first is on the log odds scale, as we see here. That is directly estimated from this logistic model. Okay, as we talked about. That is, if we increase age by 1 year, what does log odds change for the events, let's say coronary heart disease? Okay, another skill which is a little bit helpful, a lot helpful actually, is we take the exponential of beta 1. Then we will get an odds ratio. Okay. And the third skill we can use is the probability skill. We can transform back to the probability skill using the function we talk about here. So if we know beta 0, if we know beta 1, we can use this equation to get the estimated probability, right? So here's three different skills can be used differently. The log odds skill is very helpful if we use that for a hypothesis test and a confidence interval. And the exponential beta 1, which is on the odds ratio scale, is better for normal interpretation, while the probability scale is better for the prediction. Now let's talk in detail of what is odds ratio. I believe everybody knows what a ratio is, right? A ratio is one thing compared to another thing. One thing divided by another thing, right? If we think about risk ratio, it will be the risk at one condition divided by the risk at a different condition, because that's a ratio. So here, odds ratio actually is comparing two odds, right? You can think as, numerator, we have odds and one condition. In the denominator, we have odds at different conditions. So the question is, what is odds? So odds is a different measure as probability. So odds is defined as the probability of a success divided by the probability of failure. If we denote the probability of a success as pi, so the odds will be pi over 1 minus pi. For example, if we know the probability of winning this game, let's say winning a basketball game, is 50%. So the probability of fail is also 50%. So the odds will be 50 over 50. So it's 1 to 1. So the odds will have a value of 1. Similarly, if we know the probability of winning a game is 20%, so the odds would be 20 over 80, because 80 is the probability of failure, right? 20 over 80 equals 1 to 4, right? So it's also equals 0.25. Similarly, if we use the Framingham data, and we know the overall rate for the coronary heart disease is 15%. So what's the corresponding odds? If the probability of getting the disease is 15%, so the probability of not getting the disease will be 85%. So 15 divided by 85, we got an odds, which is around 0.2. Okay, this is how we define odds. So odds is originated from the sports and betting. But in epidemiology, people use odds ratio a lot too. All right, let's go back to the odds ratio. So we know what is odds, right? Odds is the probability of success divided probability of failure. And then the odds ratio is the ratio of two odds, right? So we can interpret that as if we increase the age by 1 year, what's the odds of coronary heart disease will be multiplied by? So we will look at one example shortly about how we interpret the odds ratio. Here, suppose here X is our age and the outcome is coronary heart disease. Okay. We know the odds ratio can be calculated using exponentiating the slope for age, exp beta 1, right? Suppose beta 1, our estimated slope for age, equals 0. If you take the exponential of 0, we got a value of 1, which is meaning the odds ratio equals 1. Okay, the ratio, which is two things comparing, equals 1, which meaning the odds on the numerator equals the odds in the denominator. Those two odds are the same. So back into the context of problem, no matter we increase age by 1 year or not, the odds of coronary heart disease are always equal. Okay? Think about numerator and denominator. A person who are 49 years old comparing to a person who are 50 years old, their odds are exactly the same. So what does that mean? That means there's no association between the age and coronary heart disease, right? Similarly, if we have a positive slope, right, beta 1 is greater than 0, and if we take the exponential of beta 1, we will have a value greater than 1, the odds ratio value greater than 1. What does that mean? That means the odds on the numerator will be higher than odds in the denominator, which is meaning if we increase X, the odds goes up too, right? There's a positive relationship between the predictor X and the disease, the outcome. Similarly, if we have a negative slope, exponential the negative value, we got a value less than 1, which is meaning if X increase, the odds actually goes down, right? There is a negative, or people call it reverse association between the predictor X and the outcome. Okay. One thing I want to emphasize here, when we talk about the odds ratio scale, we are on the multiplicative scale. We are not on the additive scale, okay? Which is meaning we are comparing the value with 1. If the ratio equals 1, meaning no association. If the ratio greater than 1, meaning positive association. If the ratio is less than 1, meaning reverse association. Okay. Another thing we have talked in linear regression as well is what is the odds ratio if we don't increase x by only 1 unit? Instead, we want to increase x by several units, for example, delta unit, right? So the corresponding odds ratio will be calculated as beta 1, which is slope, times delta first, then takes the exponential. So this is important. When we do rescaling like this for the logistic regression, we always need to do this first on the log odds scale, which is beta 1. Log odds scale first, then we take the exponential. Always do the rescaling first on the log odds scale, and then take the exponential to get the odds ratio. So if we do a 10-year increase, the corresponding odds ratio will be first, let's rescale beta 1 by 10, then take the exponential. We cannot calculate it as, here is the typo, it's 10 times exponential beta 1. That's wrong. We don't calculate as 10 times exponential beta 1. The correct way to do this is first rescale on the log odds and then take the exponential. We need to keep that in mind. All right. Next, let's talk about confidence interval and hypothesis testing. So we have talked about this same thing in the linear regression, right? Here, we can calculate the confidence interval for the slope beta g. And we use the same format, right? Beta g hat is point estimate plus or minus some table value times the standard error. So this formula gives us the confidence interval for the beta. Remember the 3 scales we talked about: log odds scale, odds ratio scale, and probability scale. So this confidence interval is calculated on the log odds scale, right? If we want to get the confidence interval for the odds ratio, we need to first get the confidence interval on the log odds scale, then take the exponential. Okay, always do something on the log odds scale, then transform to other scales, no matter it's odds ratio or no matter it's probability. Okay, we need to keep that in mind because otherwise that's wrong. For example, we cannot calculate the confidence interval for the odds ratio by first take the exponential of beta g and plus the z value times standard error for the exponential of g. That's wrong. Okay, hypothesis testing. We use hypothesis testing to just as what we did in the linear regression. We use a z-test. So this z-test will give us a corresponding p-values. For example, if we use 0.05 significance level, we can compare the p-values with 0.05. If you got a very small p-value, which is meaning the corresponding predictor X is associated with the outcome. So later when we talk about the so for now we only focus on the simple form of logistic regression, which only includes 1 predictors. And later we will talk about multivariable logistic regression. Then when we interpret the results, we have to see after adjusting for other variables. Don't worry, we will look at examples later about multi-variable logistic regressions. All right. So in R, we can use the same function, confidence interval function, to get the interval for the beta, which is on the log odds scale, and then we take an exponential of that to get the confidence interval for the odds ratio. All right. Any question here? All right. If no question, let's move to the example, the first example. All right. So let's first use this data set, which is the Framingham we used before. Here, let me do this. Here, I want first load the package, read in the data and prepare the data so that change all those into a factor. Okay. I run those, so you can see there are about 4,240 people in the Framingham dataset. Okay. And then our goal here is we want to know, does systolic blood pressure predict whether a participant developed coronary heart disease within 10 years? Okay. Now think about what is the outcome in these questions and what is the predictor. Okay, we want to know systolic blood pressure predict whether people develop a disease. So the outcome is if people develop a coronary heart disease. So it is binary, right? Yes or no. And the predictor, which is the systolic blood pressure, right? So before we do anything, let's get a brief idea about, on average, overall, in this data set, what's the proportion of people who develop this coronary heart disease after follow-up for 10 years. So we can do that using the count function and then calculate the proportion. So here we got among all those people participating in this Framingham program, about 15.2% have developed coronary heart disease within 10 years, and about 85% did not, right? So this 15% actually is the overall estimate for the probability of developing heart disease, or we can call it a baseline rate. Suppose anybody from this Framingham data study were picked up, right? And they asked me what the probability for this person to develop coronary heart disease within the 10 years. So our best estimation is 15%. Before we know anything about this person, before we know the age of this person, if he or she is a smoker, so on and so forth, right? So this is a baseline estimation. All right, next, because our goal is to study the relationship between the systolic blood pressure and the probability of develop a coronary heart disease. So how about we start with a plot, right? So here we can draw a plot. Horizontal axis is the systolic blood pressure, and vertical axis represents the probability of coronary heart disease, right? So we want to plot all those dots. Each dot represents a person, right? For example, here, these dots will represent people who have systolic pressure of 100 while don't have coronary heart disease. While a person here might represent systolic blood pressure of 125, but develop coronary heart disease, right? Each little dot represents a person. And then we can add a smooth line, use the loss function we introduced before. And this red line represents the estimated probability at any value of systolic blood pressure, right? So let's look at these codes. First, this line mutate CHD numeric remember CHD, right? The 10-year CHD is already a factor, right? It has two levels, no and yes. But we want to code them as 0 and 1 because no and yes, we cannot model anything. We have to recode it with value of 0 and 1. How to do that? We can use the function called as numeric. Okay, so any values, for all the levels of the factors, it will be coded as 1, 2, 3, 4, so on and so forth. We know the coronary heart disease start with level of no disease and with disease. So no disease will be coded as 1, and with disease will be coded as 2. But we want 0 and 1. So 1 and 2, if we both subtract by 1, we'll get 0 and 1. So that's what we want, right? So by doing this, we recode the outcome as 0 and 1, right? 0 meaning no disease, 1 meaning with the disease. Okay, this is this step. And then we use the ggplot. We specify the aesthetics, what's on the horizontal axis, what's on the vertical axis. And then we use geom jitter. So this is the function similar to the geo point. So let's take a look at this. So I will copy this to our R, and then I suppose we want to use geo point here. So let's look at what we got. Oh, sorry. Here is not pipe. Actually, it is plus sign. Geo point. All right. So on the right side, you can see here is the dot point, right? Because it's really hard to say the distribution because all the points are overlapping with each other. So that's why we don't want to use geo point and we use the geom jitter. Okay, let's run this. All right. Now you can see this function can spread out the overlapping points so that we have a better view of the distribution of those dots, right? And then we add a smooth line using the loss function. And the shaded area actually is the estimated confidence interval. All right, from this plot, we can see there's a positive relationship, right, between systolic blood pressure and the disease. With systolic blood pressure increase, we can see the probability of developing the coronary heart disease also increase, right? So next step, we want to fit a logistic regression. So in R, we will use a function called GLM. G is for generalized linear model. Generalized linear model. Remember, in the linear regression, we use LM, which is linear model. Here we use generalized linear model. And same as the linear regression, we specify our formula, 10-year coronary heart disease, that is our outcome, and systolic blood pressure, that is our predictor. And we specify the data. And another thing we need to add is the family option, right? Because we want tail R, our outcome, the coronary heart disease, actually follows a binomial distribution because it is yes or no types of variable. It follows a binomial distribution. And by default, the link is called the logit or the log odds, right? The logit function. If you only put family equals binomial, it also works. And you can also specify link equals logit. It's the same thing. But we can also change the link values here. Suppose we change the link as log. It gives us a new model. It is called log binomial model. Okay, it's a different model as the logistic regression. So we will not talk about this here. So here we just need to know, we need to specify the outcome which follows a binomial distribution. And for a logistic regression, we will use the length of logit because we model the logit probability, right? The log odds of probability. So all those models results are saved here, CHD symbol, and we can use the summary function to get the results, right? So this table gives us the estimated coefficients, right? The first column is the estimated beta. Second column is the corresponding standard error, corresponding z-values, and last column is the p-values. All right. All those values here are on which scale? Log odds scale, odds ratio scale, or probability scale? Think about that. Actually, that's on the log odds scale. So how we interpret this 0.024? That is, if the systolic blood pressure increase by 1 millimeter of mercury, the log odds of developing heart disease, coronary heart disease, actually increase by 0.024. And since we have a very small p-values, they're about 16 0 before 2, very extremely small. So we see it's statistically significant, right? Or we can see there's a positive relationship. But it's not intuitive, right? Log odds is not intuitive. So what we want to do next is we want to calculate the odds ratio by just takes exponential of this value. If you take an exponential of 0.024, we got the corresponding odds ratio. Similarly, we can get the confidence interval for the odds ratio. So first, we got the confidence interval on the log odds scale, then takes exponential. So here is the outcome. Now let's try to interpret those results. 1.024, that is odds ratio. So we can see if we increase the systolic blood pressure by 1 unit, the odds of getting a coronary heart disease will be multiplied by 1.024. Okay, that's the interpretation. And the confidence interval for the odds ratio will be between 1.02 to 1.0203, right? It's not a big or if we think about clinically, 1 millimeter of mercury increase in systolic blood pressure is too small, right? It's trivial. So maybe we want to report what's the odds ratio related to 10 unit increase or even 20 unit increase in the systolic blood pressure. So what we do is we can take rescaling, right, on the log odds scale, then takes exponential. So 1.6 actually is the corresponding odds ratio when we increase the systolic blood pressure by 20 units. So let's interpret this in the context of problem, right? So we say if we increase the systolic blood pressure by 20 millimeter of mercury, then the odds of getting a coronary heart disease will be multiplied by 1.6. Or we can say, well, the odds ratio will increase by 61.7 or 61.8%. Okay, that's the interpretation. Similarly, we can get a confidence interval corresponding to 20 unit increase. Again, we first rescaling on the log odds scale, then transform back using the exponential. Now we can see we are 95% confidence that odds ratio corresponding to 20 unit increase is between 1.5 to 1.7, which is purely above the value of 1, the ratio of 1, which meaning we do find the systolic blood pressure is positively associated with the odds of developing the coronary heart disease. Next, we can get the predicted probability. Now we are talking about the third scale, right? The probability scale. So we do the same thing as we did in the linear regression. First, we create a new data set where we want to predict for a person who have systolic blood pressure of 110, 130, 150, and 180, and we want to know what's the predicted probability. So we can use the function called predict, right? We put our model here. We specify, okay, we want to do the prediction for these 4 data points. And here we specify the type equal response. So the response will give us the probability. Now here is the printout. We can see for a person who has a systolic blood pressure of 110, the estimated probability of getting heart disease is about 8.7%. If the systolic blood pressure increased to 130, the probability is about 13.3%. And if the systolic blood pressure goes up to 180, the probability is much higher, which is about 34%, right? This is the interpretation. At the end, we can also create a plot to visualize the estimated probability from the logistic regression. So same as before, all those dots are just represents the original data points. And this curve is not estimated from the loss function, but is estimated from the logistic regression we just did. And the shaded area is the confidence interval for the estimated prediction. Okay. So that is the whole process of fitting a logistic regression. Let's just quickly sum up, right? We start from the research question. From a research question, we need to know which is the outcome and which is the predictor. And then we want to know what's the overall or what's the baseline probability, right? And then we want to look at what the data tell us. Before we fit any model, before we calculate anything, just plot the data and see what trend can be found from there. And then we fit our logistic model using the GLM function. And we talk about how to calculate the odds ratio and how to calculate the confidence interval for the odds ratio, as well as how we got the predicted probabilities from those models. And at the end, we can plot our model results here. That's the whole process for fitting a simple linear logistic regression. So one more note I want to talk about here, actually Dr. McLean has already mentioned this before, is in this case, we treat systolic blood pressure as a continuous variable, but sometimes some researchers want to kind of break those continuous variables into groups. For example, here, the researchers might want to characterize the systolic blood pressure into less than 120, 120 to 140, 140 to 160, or 160 or more, which might represent normal people, right? Light level of hypertension, medium level of hypertension, and severe hypertension. And then for the logistic regression, instead of using the continuous systolic blood pressure, it used the group, systolic blood pressure groups. And here we want to see those model as the better model, and we can compare the AIC. We know the smaller AIC basically tell us a better model, right? So here we can compare the AIC. We can see the better model have a higher AIC, and the one we did before using the continuous variable have a smaller AIC. So this suggests, unless it's necessary, unless there's clinical meaning, there's a biological meaning that you need to break those into categorical groups. From the statistical modeling perspective, we prefer to use the continuous variable rather than the grouped variable because this is kind of collapse some information. Here, there's assumption that we assume people have blood pressure of 120 to 140 are exact the same. And we assume any participants within each group is the same. That's a big assumption. So again, unless there's important reason you want to do that in your research, you can use group. Otherwise, it's better to use the original continuous variable scale. Okay, so we will stop here for 15 minutes break and we'll come back around 11:15. Thank you. Please let me know if you have any question about the previous topics. And after you got back, let's talk about multiple logistic regression. Okay. Let me share my screen and we can look at the lab exercise. So we will move the afternoon lab question 1 to 2 in the morning session. Okay. So if you look at this HTML file, again, we will, this is another example, which is similar to what we just looked at during the lessons. So again, we will use Framingham big, but here, instead of looking at the systolic blood pressure and coronary heart disease, now we look at the age and coronary heart disease. And we want to see the relationship with age increasing, what happens to the probability of disease, right? So we can do the same thing. We can start by plotting our data using the ggplot2 function that we talked before. And from this plot, we can see there's a clear positive relationship. As age increase, the probability of getting a coronary heart disease also increase. And then we can fit the model using the generalized linear model function, right? Outcome, again, is coronary heart disease. Now the predictor is age. And we specify the distribution, which is binomial. And here is the model results. We have the coefficients models, right? This is the estimated slope for age, which is 0.07, which is meaning if we increase age by 1 year, the log odds of getting coronary heart disease increase by 0.07. And we have a very small p-value, which is meaning it's statistically significant, right? But we can get a more intuitive interpretation rather than on the log odds scale. So we want to calculate the odds ratio simply by take the exponential of 0.074. And we got odds ratio of 1.078. And we can also get the confidence interval for the odds ratio. Right? And now we can interpret those, right? We can say with 1 year older, the odds of getting coronary heart disease will be multiplied by 1.08. And we are 95% confidence the odds ratio will be between 1.07 to 1.09. That's the whole interpretation. We can also get a corresponding odds ratio by increasing 10 years, right? So we first rescale on the log odds scale, then take the exponential. So here we got odds ratio of 2. So with 10-year increasing in age, the odds of coronary heart disease almost doubled, right? And we can also get the confidence interval for the odds ratio related to the 10 years increase in age. All right, next, we can draw the estimated probability curve, which is estimated from our simple logistic regression. We can add those curves in our plot. And we can also get the predicted value for a person who are 35, 45, 55, 65 years old. Okay. Now we use the function called predict and type equals response. Now we can see for a person at age 35, about 5% the probability of getting a coronary heart disease. And at age of 55, the probability of getting coronary heart disease increased to about 19%, right? And at the age of 65, the probability is about 33%, about 1/3. All right. So you can change the codes here. And now let's work on exercise 1 and 2. Okay. First exercise, you can use the count function to get the proportion of coronary heart disease in people who are smokers and the probability of getting coronary heart disease in people who are non-smokers. Then let's fit a logistic regression where the outcome is the disease and the predictor is current smoker. And then we got the odds ratio and 95% confidence interval for the odds ratio. We can skip the part D for now. Okay. And for exercise 2, we can continue at for exercise 2, it's a different data set. It's a different variables, excuse me. So exercise 1 is between coronary heart disease and smoking. Exercise 2 actually is between coronary heart disease and systolic blood pressure. So part A asks you to add a smoother using the loss function on the scatter plots. And then part B, we can fit a logistic regression where outcome is coronary heart disease and the predictor is systolic blood pressure and get the confidence interval and the odds ratio. And part 3 asks you to get the confidence interval, to get odds ratio and confidence interval for a 20-unit increase in the systolic blood pressure. And part D asks you to draw such estimated curve as we did here to our plots. So now let's work on this lab exercise. And then in the afternoon, we will talk about multiple logistic regression. Please let me know if you have any question. You can text your question in the chat box, or you just unmute yourself and speak up. Fitting a logistic regression in R. So for the afternoon, let's start with what we left for the lecture. I'll share my screen and so I want to introduce you another way to calculate the odds ratio. Especially, so this is only works if we have a binary predictor. So we know the outcome is binary, right? With the disease, without disease, survive or died. This is binary outcome. But if we have a binary predictor, for example, use the drug, not use the drug, smoker, non-smoker. In this case, we can summarize our data in this called 2x2 table. Okay, so for this little table, you can see we can summarize among all the samples how many people who take the drug and experience the event, which we denote as A. And there are about B many people who take the drug but don't experience the event. Similarly, we can have C participants who didn't take the drug but experienced the event, and D of them didn't take the drug and don't have the events, right? We can summarize our data in this little 2x2 table. And then we will have a very nice, simple formula that we can use for the hand calculation to get odds ratio, which is the A times D over B times C, where A is just the counts, right? When we use this method, we need to make sure first, the way we set up our 2x2 table, we need to make sure the first column of the table always denote the events or the success, all right? And we also want to make sure the first row of the table denote the exposure. When we talk about exposure, we mean the things we care about. And the other level, no drugs, is the reference group. So in other words, we will get the odds ratio comparing people take the drug versus people who don't take the drug. So people who don't take the drug is the reference group, right? We want to compare the odds of event in people who use the drug versus the odds of events for people don't use the drug. So people don't use the drug is reference group. So when we set up this 2x2 table, make sure the first row represents the non-reference group, the exposure level, and the first column represents the success or event. And then we can use this ABCD formula, right? Which is AD over BC. So let's look at one example here. Now, suppose this is for example, a clinical trials. We have 200 participants or patients which are recruited for these clinical trials, and we randomly put them into two groups. One take the drug, the other group don't take the drug or use some placebo drugs. Together there are about 400 people, and 20 of them are randomly assigned to people to take the drug group. And we follow them for, let's say, a week and see if some event happens. And among those 200 people who take the drugs, 20 of them experience this event and 180 don't. So A would equals 20, B would equals 180. Similarly, for the other 200 people who did not take the drug or take some placebos, there are about 50 had the event and another 150 didn't have the event. Now, if we calculate the odds ratio, which is odds ratio of the event, comparing people who take the drug versus people who don't take the drug, we can use this little formula, A times D over B and C. So it will be 20 times 150, right? A and D, over B, which is 180, and C, which is 50. And the odds ratio is about 1/3. So how we interpret this? We can say, okay, the odds of the events for people who take the drug is only 1/3 of the odds for people who don't take the drug. So in other words, the drug is effective, right? The drug reduces the odds of events. That's a good thing. So of course we can fit a simple logistic regression to get the same odds ratio. So here I just introduce a simple way, a different way of how to calculate odds ratio using this little formula. So as I said, it only works if you have a binary predictor. suppose if you have a continuous predictor, sorry, we cannot use this little formula. And if we have a categorical variable, but more than 2 levels, for example, the BMI groups, we might have normal BMI, overweight, or obese, right? We have more levels. And again, we cannot use this little formula. Another thing we might be careful is the design of how we collect this data. In these examples, where the people are independent to each other, right? So, in other words, people who take the drug will be totally independent from the people who don't take the drug. But sometimes there are some matched designs in the clinical trials, and in that case, the independent assumption is not satisfied, and then we cannot use this formula. We have to use a different odds ratio calculation. All right. So from here, I think you can work on the exercise 1D part. So this one. So basically, we first fit a simple logistic regression, use the GLM function, right? And then we can now use this little formula, AD over BC, and you will see we can get exact same results. So here, let me show my screen here. So here, first we calculate, we fit a simple linear, simple logistic regression, right? Outcome and exposure, current smokers. And we can look at the summary of the results. So point 1, which is the estimated on the log odds scale. To get the odds ratio, we need to take the exponential, right? So the odds ratio related to the smoking status is about 1.114. That's what we estimated from the logistic regression. Now, let's use the little formula. So first, let's create these 2x2 tables. All right. Now, remember when I said make sure, right, the right format, the right setup for this 2x2 table. Because here, if we think smoker is the non-reference group and non-smoker is the reference group, our little 2x2 table shouldn't be this way. So let's write the correct 2x2 table. Okay. 2x2 table. So we want this is coronary heart disease, yes, and coronary heart disease, no. Right? And on the rows, we want to denote the smokers and non-smoker. So how many people are smokers and also had coronary heart disease? If you look at here, it is 333. Smokers and no disease, 1762. Non-smokers with the disease, 311. And the other is 1832. All right. Now we can use our little formula, which is 333 times 1834 divided by 311 times 1762. So if we calculate that in R, now we get 1.1145. Now you will see it's exact the same number as what we got from the logistic regression, right? All right, so now you may ask, since we can use this formula, do the hand calculation, why we bother to fit a logistic regression? Well, logistic regression is much better in a lot of area compared to this little formula. First of all, remember this formula only works if we have a binary predictor. In this case, is smokers and non-smokers. Well, it does not work for other categorical variables and does not work for the continuous variables, right? And another thing is for the logistic regression, we can add more than one predictors in our model, right? We can study multiple predictors at the same time. So that's what we call multiple logistic regression. All right. Similar to the multiple linear regression where we can put multiple predictors, x1, x2, x3, so on and so forth, in this model. Same here. For multiple logistic regressions, we model the log odds in the linear combination of all these predictors, right? So x1 could be age, x2 could be sex, x3 could be BMI, x4 could be systolic blood pressure, so on and so forth. All right, so let's think about what's the possible reasons why we want to fit a multiple linear regression. So why we want to fit a multiple linear regression? So I can think about three major reasons why we want to fit a multiple logistic regression rather than a simple logistic regression. First is for a simple logistic regression where we only have one predictor, we can only study the relationship between this specific predictor and the probability of events. But for multiple logistic regression, we can study different multiple predictors at the same time. We can study age, BMI, systolic blood pressure, exercise, heart rate, so on and so forth together with the probability of outcome. That's the first thing. Second is if we think about the example we talked about yesterday afternoon, where we want to build a model, which this model can give us the prediction, right? So for example, we want to predict the probability for a person to get coronary heart disease with using only his age information. Do you think it will be a good prediction model? Okay, we only predict a person's probability of getting coronary heart disease using age information. Probably not a good model. We should consider other factors. We might consider the age, the gender, the family history, or even genetics, or smoking, or BMI, right? All those together will make our prediction a better prediction, a more appropriate and a more accurate prediction, right? That's the second reason. Third reason, I think is a very important reason, is the multiple logistic regression can be used to address the confounding issues. So here I talk about the word confounding. So let me try to write something here. Okay. Confounding. So this is a very important topic when you build a model or when you do your analysis. All right. So let me first give you some idea about what is confounding. One of my favorite example of confounding is the ice cream sale, and sunburn rates, let's say, in a population. So suppose a group of scientists find the higher ice cream sales associated with a higher sunburn rate in a certain population. Do you think that's really the effects of ice cream sale? In other words, do you think the ice cream sale is really positively associated with sunburn rate? Probably not. If we think deeper, we might know, okay, maybe the temperature. Because when the temperature is high, for example, June, July, August, people tend to buy ice cream, right? Ice cream sales would be high. And during these summer times, people expose more to the outdoors and get more sunshine and the sunburn rate goes up. So the relationship between ice cream and sunburn rate actually is spurious. Oh, right? It is caused by temperature. So we see temperature confound the relationship between ice cream sale and sunburn rate. Temperature is a confounder. All right. Let me share another example about confounding. That is, researcher find a sex difference. Okay, a sex difference in terms the probability of develop malaria. Okay, people find males tends to have a higher probability or higher odds of develop malaria. But do you think there's any biological reason? For example, the hormone levels different, or maybe some uh, genetic or issues? No. So actually, if you think about that, outdoor occupation, okay, could be a confounder, right? Males tends to be more likely to have outdoor types of work, and outdoor meaning has a higher probability of exposed to mosquitoes. And we know mosquitoes is the how the malaria spread, right? So again, the relationship we found between sex and malaria is confounded by the outdoor types of work. Okay, so here's another example of confounding. So from these two examples, we know for a confounder, it must associated with the thing we want to study, right? The predictor. And it also associated with outcome, right? Temperature, which is confounder, associated with the predictor, ice cream sale, and also associated with the disease, which is the sunburn rate. All right. And let me give you a definition of what we used for confounders. So a confounders needs to be associated with both exposure and disease. And the confounder is not in the causal pathway between the predictor and outcome. Okay, that's the definition of confoundings. All right, so why we see multiple logistic regression can deal with confounders? Before we talk about that, let's just think about the mosquito examples here. Okay, how we remove the confounder due to the outdoor types of work. Okay, you may think, what if we only compare the rates of malaria, right, between male and female in people who work indoors? Okay, we only want to compare their relationship for people who is indoors. And then we see, their relationship still exist? And then we can focus on people who work outdoors. Among those people, are their relationship between sex and malaria still exist? If the answer is no, then we know outdoor is definitely confounder, right? So what we did here is we kind of stratify the outdoor into indoors and outdoors and look at different levels, right? So here for the ice cream and sunburn example, we can fix temperature at a specific level or a specific range. So, okay, for temperature at this range, are there relationship between ice cream and sunburn rate still exist? Right? So you will see to remove the confoundings. One way to do that is to put the confounder at a specific level or at a specific value. Right? We control the value of the confounder. Then we study the relationship between outcome and predictor. That's the way we deal with confoundings. Actually, that is what multiple logistic regression can help us. Actually, not only multiple logistic regression, but also multiple linear regression, multiple Poisson regression, multiple Cox-PH models. All kind of regression approach is the same. The multiple variables, they can help us remove or reduce these confoundings. Why? Let's look at how we interpret the beta coefficients, right? The beta, for example, beta 1. So when we interpret beta 1, that is with 1 unit increase in x1, how much of log odds increase, right? But the key is here, okay, holding the other predictors constant, which is meaning, okay, if for x2 until xp, they are the exact same value, then if we change x1 by 1 unit, what happens? So holding the other predictor constant is just like we hold the temperature the same, or we only look at people work indoors, or we only look at people work outdoors, right? And then we look at the effect of the x1, which is beta 1, right? Similarly, if we take the exponential of beta g, we got odds ratio, right? It's the odds ratio associated with 1 unit increase in x, holding the other predictors constant. Okay, make the other variables the same. What happens if we increase xg by 1 unit? Sometimes people say holding the other predictor constant. Some people just say controlling for other predictors. Or people can say adjusting for other predictors. It's just exactly the same thing. Just keep those the same. What happens if we change x1 by 1 unit? Okay. To me, this is the very, very important reason why people want to fit multiple logistic regressions. Because if we ignore those confounding issues, the result we got is fake. For example, the association between ice cream and sunburn rate, that's spurious. And also the sex difference that found in terms of malaria development is also spurious, right? So we need to consider these potential confounders to get an unbiased result, unbiased association. All right. So now let's move to our second example. By the way, any question here? Okay, so let's look at our second example. Our question, okay, our research question is, we want to know the effect of age on the cholesterol, on the coronary heart disease risk. Okay, after removing all other risk factors, the influence of all other risk factors that mixed up with age. Okay, what does this sentence mean? Again, first, we need to find out which is the outcome, which is the predictor, the main predictor, or we call it exposure. Okay. The outcome is coronary heart disease, which is yes or no, binary outcome. And the predictor, or the main predictor, or the exposure, that's the thing we care most about, is age in this case. How about the second half of the sentence mean? That means we need to remove any confounders between age and cholesterol heart disease. We want to controlling for these confounders or adjusting for these confounders. Okay. All right. So basically, what we're gonna do is first we need to know what those potential confounders are, right? We find out those potential confounders, then we adjust for them in the logistic regression. How we adjust for them? We just put those in the multiple logistic regression, right? All right, so the first step, we want to find out the potential confounders. Okay, how to find the potential confounders? How can we do that? Let's go back to the definition of confounders. Remember, confounders needs to be associated with what? With predictor and associated with outcome. Confounder needs to be associated with predictor and associated with outcome. All right, now let's look at in our data, which variable are associated with the predictor age. So how we do that? Maybe we can plot our data just as we did before, right? So for a continuous variable, like systolic blood pressure, diastolic blood pressure, total cholesterol, BMI, heart rate, glucose, all those are continuous variable, right? We want to know which one are associated with age. Because if they are the true confounders, it must be associated with age. So we can add a smooth curve, right? Use the loss function and to get an idea of the relationship. Now, here is the plot. From this plot, we can see BMI. I would say it's a weak association, right? Diastolic blood pressure may go up, then level off. Glucose, I would say it's a weak association. Heart rate is almost parallel. I would say probably there's no association with age. Systolic blood pressure, yes, we can see a strong relationship with age, right? With age increase, systolic blood pressure goes up. And for the total cholesterol, we can see, yeah, it goes up, and at the end it goes down a little bit. But Dr. McLean has explained this part could be due to some selection bias, because people who survive at an older age might have a smaller total cholesterol levels. So from these six plots, we might see probably systolic blood pressure and total cholesterol level. These are pretty have a pretty strong relationship with age, right? Okay. So what about categorical variables? So for categorical variables like the smoking status, how do we know the smoking status is related to the age? So we can compare the average age between smokers and non-smokers. So we can we find among smokers the average age is about 48, and for non-smokers, which is older, so smokers tends to have a younger age. Yeah, so I would say it looks smoking status is related to age. Similar for the diabetes. For people with diabetes, the age is older, which is 55, comparing to 50 for people without diabetes. So I would say yes, diabetes might also associate with age. How about gender, male and female? We can say for male about 50 on average age, and in males the same. So the age distribution is pretty balanced between male and female, right? So I would say sex may not associate it with age. All right, so let's summarize this first step. Okay, this step, we want to explore which variables are related to the predictor age. For continuous variable, we will select systolic blood pressure and total cholesterol. And for the categorical variables, we will select the carbon smokers and diabetes. Okay. All right. For those 4 selected variables, we need to know which one also related to the outcome, right? Because that's the definition of confoundings. Confounders needs to be associated with predictor, needs to be associated with the disease. All right, first step, we figure out who is associated with the predictor. And then the second step, we'll say, okay, among those we selected, which ones also associated with the disease. So let's look at the smokers. And from this, we can say among smokers, the probability of developing the coronary heart disease is about 16%, compares to 14.5% in non-smokers. I would say yes, smokers is related to the coronary heart disease. How about diabetes? Oh, it's even more dramatic, right? For people with diabetes, about 37% probability compares to 15% for people without diabetes, right? Yeah, definitely diabetes will be related to the coronary heart disease. How about the continuous variable we have selected in the first step, which is systolic blood pressure and cholesterol, total cholesterol level. So we can just do the same thing as we done in the previous step, but now we can the vertical axis is the probability of coronary heart disease. Okay, so we can see a clear increasing or positive relationship between the systolic blood pressure and the probability of coronary heart disease, and similar for the total cholesterol. So to summarize all this in the table, we can just say, does systolic blood pressure related to age? Yes. Does it related to the disease or the outcome? Yes. So is this a potential confounder? Yes. Right. Same for total cholesterol, current smoking status, and diabetes. How about BMI? We know for BMI, it is the slope looks flat right here. But for the BMI, the relationship between BMI and age looks flat, and also it has a vague association with the outcome. So from the perspective of being a confounder, we would say BMI probably is not a potential confounders. Okay. Okay. Now we know when we do our analysis, we should consider the confounders of systolic blood pressure, total cholesterol, smoking status, and diabetes. And we will put all those variables in our multiple logistic regression. Okay. How about BMI? So for now, let's just keep BMI in our model, and later we will decide if we really need BMI or not. Okay. So any question here? All right. So what we're gonna do next is we will fit 2 models. The first model is called unadjusted model. Or people call it crude model. So that is the model with only the main predictor, which is age. Okay. We did not consider the potential confounders with only the outcome and age. Now we see this model, unadjusted model. Okay. So we see, first of all, we just keep whatever variables we will use in the data. We will use our outcome, right? Age is the predictor. and the potential confounders is all those. We only need these variables, so we only keep those. And we remove all the missing values. So we can save the new data sets called Framingham_CC. So this will be a smaller data set, which only include 1, 2, 3, 4, 5, 6, 7 variables, and without any missing data. So we will use this Framingham CC as our final analysis data set. And we can see about 68 subjects were removed due to missing values of either of those variables. Okay. And then with this final analysis dataset, we want to fit a simple logistic regression, and we calculate the odds ratio as well as the confidence interval for the odds ratio. Okay. Here is the results. So how we interpret these results? We can see with 1 year additional, with age increase by 1 year or with 1 year increase in age, the odds of coronary heart disease will multiply by 1.08, right? That's the interpretation. All right. What about our adjusted model, which means the model considering all those potential confounders? So we can add all those potential confounders in our model. And then we can calculate the odds ratio as well as the 95% confidence interval for the odds ratio. And we can get the age, or we can got the age effect. The odds ratio is 1.068, and here's the confidence interval, but those are adjusted odds ratio. Okay. When we say adjusted, we mean if we keep the smoking status the same, and the same level of systolic blood pressure, the same level of total cholesterol, and same diabetes status and same level BMI, what happens if we increase age by 1 year? Okay, that is what adjusted means. And then we want to compare the odds ratio from the crude model, the unadjusted model, and the adjusted model. So what did you find? Unadjusted model gives us 1.08, and adjusted model gives us 1.07. So we find the adjusted model have a smaller magnitude, even though it didn't change too much. But if you think the direction, it goes down. So what does this mean is if we consider the confounding effects of smoking, systolic blood pressure, diabetes, BMI, the adjusted effects of age actually is smaller, right? It's smaller. Why is that? Because we know the older age tends to have a higher blood pressure, while high blood pressure tends to have a higher risk of coronary heart disease. So this creates a spurious relationship. So make the crude relationship between, so it makes the age effect larger, right? If we didn't control for the blood pressure, the effects we estimated actually is larger than the truth. Okay? Similar, older people tends to have a higher cholesterol level, and we know a higher cholesterol level is related to a higher coronary heart disease. So again, we need to consider those parts. So in practice, it's not always the same. It's not always the adjusted effects has a smaller magnitude compared to the unadjusted. So it really depends on the association between the confounders and it really depends on the association between confounder and the predictor and confounder and the outcome. Okay. And in your afternoon lab, which you will do now in the exercise 3. In this example, you will find actually the unadjusted odds ratio actually is so you will find the adjusted odds ratio will become bigger in magnitude comparing to the unadjusted odds ratio. Okay. So last question. Remember we put BMI in our model. If you go back to the little summary table, we know BMI probably is not a potential confounder, but we still keep BMI in our model. Now our question is, do we really need BMI in our model, right? So similar to yesterday when we comparing different models, here we can compare a model with BMI and a model without BMI. And let's see which one is better or how many difference comparing this model happens. Okay. So here we fit another model by removing the BMI, and we'll save it as chronic heart disease no BMI. Now we use ANOVA function to compare the model without BMI and the model with BMI. But here we use a test called likelihood ratio test. So in yesterday's lecture, we have used the ANOVA. Let me search for ANOVA. Yeah, we have used a ANOVA function to compare two models, but the ANOVA gives us a f-test. Okay, that's for linear regression. So for logistic regression, we use the same function called ANOVA, but we specify we want to use likelihood ratio test. So this test is based on the likelihood ratio. All right, so this is the result. Okay, it compared two models. Model 1 without BMI, Model 2 with BMI, and the p-value gives us 0.21, which is pretty large. So that means we don't have enough evidence to say that these two models are different to each other. So in other words, we think the model with BMI does not improve the model much, right? If we can make our decision purely based on this likelihood ratio test, we prefer model 1 because it's a simpler model, right? So another thing we can compare whether we should keep BMI in our model is to compare the odds ratio of age, which is the main thing we care about. We care about the effect of age. So we want to say, okay, if we add BMI in our model, what's the effect of age? If we remove BMI from the model, what's the effect of age? Does that change a lot, right? So here we can see with BMI, the effects of age, which is measured by odds ratio, is 1.07, and without, it's also 1.07, barely, almost no change, right? So this is also indicate maybe we should use model 2, the one without BMI, because with or without BMI, the age effect does not change too much. So in practice, we can use the 10% rule to decide if the odds ratio is large enough to be considered. Okay. In this case, no, we don't need BMI. So based on those two perspectives, based on the log ratio test and the change of the effects of the main predictors, based on those two, we make our decision to remove BMI in our final model. Okay. Suppose log likelihood ratio test suggests no difference, no big difference. but we do find a big change in terms of odds ratio. Do you think we should keep BMI in our model? I would say yes, we should consider that. And similar, if the age, the odds ratio of age does not change too much, but but the test suggests these two models are different. In that case, we also should keep BMI in our model. Okay. So at the end, our final model would be the adjusted model, but without BMI. So we can summarize our results in this little table where we can report odds ratio as well as 95% confidence interval. Okay. So I think I will stop here and we can work on the exercise 3, where we want to model the relationship between cholesterol, coronary heart disease, and smoking status. Okay. Now, in the first step, we need to fit a crude model, which is unadjusted model. While in part B, we will fit a adjusted model where we put age, where age will be the potential confounders. And in part C, we will compare the odds ratio that we observed from model 1, model A, and model B, and see is odds ratio of smoking change a lot? Should we use the adjusted model or should we use the unadjusted model? And in part D, we will compare these two models using the likelihood ratio test. Okay, let's see part C and part D get the same conclusion or not.